Hello everyone and welcome. Today we will talk about about something called linear independence. So we start off by declaring that we stating that there is a vector space V. This is our vector space, and we have a collection of objects inside this vector space as, let's say, this vector space V consists of the following objects. It's a set of, let's say, 1, 2, 3, n. It's a set of these objects, and we define these objects to be linearly independent. That is, we call them linearly independent if we have a combination that looks like the following. And if this combination is trivially satisfied, that is, if you expand this and all the coefficients, that is a1, a2, a3, an, all of them have to satisfy this equation, and for that, if they are trivially satisfied, that is all the a's are 0, then these objects over here that is appearing in the set of this vector space, they are called linearly independent. So what do we mean by this? Let's try to see it explicitly. So let me choose a deep color again and a bit wider stroke. So what we mean is that, let's say I had this n objects, right? So we had our condition as I equals to 1, starts from 1, ends at n. This is ai and this is I, and this had to satisfy this, that is all the linear combination, of the objects from the vector space, that is the vectors, they equal to the null vector. So if I write it explicitly, it will be a1 1, a2 2, a3 3, and so on up to an n is equals to the null vector. And if all of this a1 equals to a2 equals to a3 equals to a of n equals to 0, this is the condition. This is the condition we are calling the trivial case. And if this is satisfied, then we call these vectors, that is, then we call the vectors 1, 2, 3, n to be linearly independent. Because if there is a non-trivial combination that gives rise to this null vector, we call them linearly dependent. That is, if this condition is not satisfied over here, that is, if this is not satisfied. So let me write this again. If this is not satisfied, then we call the vectors to be linearly dependent. So this is how we can define the linear dependency and independency. Now let's try to see another example. So we call this thing, let's say, example. So in our example, we want to take 1 as a column vector, and in this example, let me just write it in a few words. In this example, we are considering a vector space over Kn. So this K is our field. You can say from these entries that this K is just R, so instead you could write Rn. That is, the entries will have n tuple of numbers associated with it. So this is the side note for our example over here. So 1 is like this, and then 2 will be given by 0 1 0 dot 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 dot, and similarly the nth will be, nth vector will be given by, there is a this is the last one, so this will be given by 1. There is a 1 in the last entry. So now let's consider the linear combinations, that is a1 1, a2 2, a3 3, and dot 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 plus an n, which is equals to the null vector. And this null vectors, we can represent it as a column, and it will have n number of zeros. So expanding this gives us a1 a2 a3 dot 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 an equals to 0 0 0 0 dot 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 0. So from here we can conclude that a1 is 0, a2 is 0, a3 is 0, and so on. That is, all the coefficients are 0, and as a result we can say that these vectors 1 0 0 dot 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 0, and let's give a set symbol over here, this 0 1 0 0 0 0 0 0 1 0 0 0 0, these are linearly independent. Now we want to take a look at another example of linear independence. Let's take, this is example 2. Let's take a matrix given by A, B, C, and D, a 2 cross 2 matrix. Again, we can decompose this into the following way. and here this 1 ket is denoted by 1 0 0 0. Similarly 2 will be given by 0 1 0 0. 3 will be given by 0 0 1 0, and 4 will be given by 0 0 0 1. So the question is, are these vectors linearly independent, that is 1 2 3 and 4? It turns out that yes, they are linearly independent, because the only way this matrix, that is this combination, would be a 0 vector, and this combination would be a 0 vector if and only if all these ABCDs are 0. So here what we mean by that is we had a matrix called ABCD, right? And this ABCD is just the matrix representation of this form. Let me just highlight it out. So this corresponds to this matrix, and this 0 vector here, this null vector over here, would actually correspond to a 0 matrix. So if we assume that this relationship, let's call this equation 1, if we assume that 1 is true, then the only way this is true is that A, B, C and D, all of them have to be 0. So these guys over here, that is this object 1 2 3 and 4, they are linearly independent. So we talked about what is linear independence, and if the vectors are not linearly independent, they are called linearly dependent. So with that, we want to move to our next discussion, and that is called the basis and the dimension of a vector space. So before going to basis, let's talk about dimension of a vector space. So we saw that a vector space that had n objects, that is n vectors, and these vectors could be linearly, linearly independent or linearly dependent. Now the case we want to talk about is that what happens if this vector space, which contains these n objects, that is n vectors, and all of these vectors are linearly independent. So we say that if a vector space that is defined over a field has n linearly independent vectors, then the dimension of that vector space is n. So what do we mean by that? Let's write it down. So we have a vector space. This serves as a it's a remark. This serves as a definition for the dimension. So let's just write dim. It's a shortcut notation to represent the word dimension. A vector space that is defined over a field, let's say K, has a dimension n if the vector space contains n linearly, okay, let me choose another color so that you guys may understand well. If the vector space contains n linearly independent vectors, and we denote it that vector space as, let's try to write a calligraphic V. Okay, it doesn't look like a calligraphic V, so let's just go with the V of n, and we write the field K. So if K is R, that is the real number, then we write it as V of n R, and this is a real vector space, and if the field K is just the complex number, field of the complex numbers, we write it as V of n C. It's called a complex vector space. So my field, the elements that are coming from the field, they are complex numbers. So how do we find the dimension of a vector space? The definition suggests that we look for the linearly independent vectors. So again, let's take our example of the matrix that we saw, A, B, C, D, and we wrote it as A1, B2, C3, D4. So we saw earlier that this 1, 2, 3, 4, there are 4 vectors, or so to say 4 objects in that vector space, and they are linearly independent of each other by the definition of linear independence. So from here we can say that this 2 by 2 matrices gives rise to a vector space of 4 dimension. Because there are 4 linearly independent vectors over here. So that's why we are getting a 4-dimensional vector space. And from here we can have another idea that is called a basis. The idea for the basis actually comes from the linear independence of itself. And in the next lecture we will talk about basis of a vector space, and we will see what we can do with it. This will be it for today, and thank you.